Hey physics peeps. So 33.4 to 33.7 notes. Ready? Okay. So we're starting off with electric potential energy. So just like we talked about things that have gravitational potential energy, so like the higher up they are, the more energy they have, electrical charges can have potential energy as well. So the way that we measure that, and so the electric potential energy of a charged particle increases when work is done to push it against the field of the thing that charged it. So basically, it's like if you were pushing a positive charge forward in a positive field. Okay? That's doing work. And so that energy that charge has due to its location in the electric field that it's in is called its electric potential energy. So just like gravitational potential energy was its position relative to its starting place, it's the same thing with electric. It depends on its position in the electric field. Okay? So there's also electric potential, and this is different from electric potential energy. I know it is confusing, not my fault. So electric potential is the electric potential energy per charge. Okay? So we measure that with the unit called the volt, V-O-L-T, and that is equal to 1 joule per coulomb. Joule is our measurement of work, and coulomb is our measurement of charge. So electric potential energy per charge. Okay? So volt, commonly called voltage. Our book uses them interchangeably. So when they're talking about voltage, they're referring to a volt. Once you find the 0 voltage spot, you can assign a value to any location in your electric field, even if there isn't a charge there. So basically, you know that in this location, you're going to have a voltage of this, and in this location, you're going to have a voltage of this, even if you don't have anything there, which is kind of cool. So, high voltage. We're going to talk about this in a couple of chapters again, but high voltage requires a lot of energy only if there's a large amount of charge involved. Okay? So for example, your rubber balloon on your head, you charge it all up. And it can actually be charged to several thousand volts, which sounds like a lot. And it is a lot. But the charge on that balloon is very, very small. It's less than 1/1,000,000th of a coulomb. A coulomb is actually a pretty significant amount of charge. And so the energy associated with the charged balloon is really, really small. So even though our voltage number seems really high, it's not considered high voltage. So you can store electric energy. And we store this in a device called a capacitor. You may or may not have heard about these before. I don't know. So, these are in basically anything that has an electric circuit in it. And the simplest form is just 2 conducting plates that are separated by a small distance but are not touching each other. All right, basically one stores a bunch of positive charges and one stores a bunch of negative charges. And the energy that's stored in the capacitors comes from the work that is done to charge it. Okay? So, bear with me. We're on slide 5. So, when those plates get connected to a battery, the positive terminal on the battery basically removes all of the electrons and pushes them to the other plate. Those charges just kind of cycle through the battery, up and over. You can see in that picture there. And so that charging process is done when the potential difference between the plates equals the battery's voltage. So batteries have different voltages, you know, a 6 volt, a 9 volt, that kind of thing. So a lot of the time, there's a picture in your book. If you have your book, it's on page 672. Otherwise, you can Google pictures of capacitors if you really want to look at them. But a lot of the times, they are just a little metallic thing. They're really like 2 plates rolled up, and then they wrap some plastic around them. And they usually use different colors to differentiate the different sizes of them. And they just have 2 wires sticking out. They kind of look like little bugs, almost. So, slide 6 and 7. Talking about something pretty cool. Van de Graaff generator. This is the big ball thing that has the belt that spins, and when you touch it, it makes your hair stick out. So, the Van de Graaff generator, hollow metal sphere, that's on an insulating stand. Okay? So, there's a belt that runs from the top of the sphere all the way down. Belt goes by some needles that fluff off electrons to it. Belt runs those electrons to another set up in the sphere, and that another set of needles up in the sphere. They scrape all those electrons off. Those electrons try to get away from each other, so they all go to the outside of the sphere. And then when you touch it, those electrons come to you. They get on your hair. Forces them to repulse, your hair sticks out. So you can up the voltage on a Van de Graaff generator by increasing the radius of the sphere, so making the sphere bigger. Or you can put it in a container with high pressure gas. There's some fun gas law-y things that can happen there. But there you are. So slide 7 is just showing you the inside of the Van de Graaff generator. So you can see the metal forks at the bottom of the base, and then at the top, that's where all the electrons get deposited and whatnot, and then they just end up on the outsides. I'll try and find some videos to post for you, but other than that, I will talk to you later.